So yeah, so let me do it again, although it sounds like I'm repeating myself a little bit, but let me try to tell the story slightly differently than I told it before, but that would clarify some of these questions. So I wrote down again the Virasoro algebra. Let me do it one more time. And it's a Lie algebra. Do you know what? Let me call this 1 over h bar n cubed minus n delta n plus m. And then if I do this rescaling, I can actually secretly put the h bar here and then put the h bar there. So suppose that I give you this commutation relation. The symmetry that I'm talking about is the symmetry of diffeomorphisms of the circle. So I have this thing, it's called diff S1, diffeomorphisms of the circle. And it turns out that this thing has a structure. And what I'm going to do is I'm actually going to look at all the diffeomorphisms that don't include the transformations that look like this. So I'm actually dividing out those transformations, okay? So I keep only this. It turns out that this thing has the structure of a phase space. And the formulas for explicitly writing it, so indeed if I do it in this notation with the u's, why not? I have a little u, and it goes to a big U of u. This is the diffeomorphism of the circle, if u is periodic. And if I do it modulo these transformations, then I have an element of that. Meaning that the fact that it has a structure of a phase space actually means that this is an even dimensional manifold, where I can point to a number of things that I can coordinates and a thing that I can call momenta. Now, here I'm going to write down a very schematic equation, and I'll put quotation earmarks marks around it. So there is some kind of object, some kind of coordinate system that I can put on this thing. And I can call some of those coordinates Q, the other one's P. And there's a bunch of Q's that are paired up with a bunch of P's. And I get a commutation relation between them. And the claim is that I can write down a particular symplectic form, this thing is called, on this particular space, such that if I define the following functions, and I briefly had this thing on the board. This is big U and this is little u. So I integrate over the circle the Fourier modes of this thing. And I would do the computation that I would normally do in order to go from a symplectic form, which gives me a Poisson bracket, to commutators. There is a symplectic form such that if I take these objects, that they satisfy that algebra. Okay? So, and actually, they do even more. What they do is they compute they generate this algebra, and they give me even a representation on the algebra. And it turns out that if I take this particular, this is called a coadjoint orbit, but it's an orbit of the diffeomorphism group, I'm going to get the vacuum representation. Meaning I'm going to get the representation that just counts the number of states in the Hilbert space obtained by precisely by doing this, where I take all the states that are obtained by acting with a bunch of L minus ones. So I take a string of these L minuses and I let them act on the vacuum. And I can take the space of all these states. I called that previously H, in this case I would call it H0. It's the space of the vacuum state with all the descendants. That Hilbert space describes the quantization of this space with that symplectic form. And this algebra acts on that space. Okay? So now let me use that fact to compute that object. So it turns out that basically computing this thing can be done even just by knowing this abstract nonsense. I don't even need to tell you what that thing is. I'm just telling you this thing is such that it gives me the Virasoro algebra. Now, but in order to make this particular statement that this thing satisfies that algebra, I can try to do a path integral definition of the quantum mechanics. And then the way this typically works is that if I have a symplectic form, the way I have to do the path integral is to use the measure that's appropriate to that particular symplectic form. Yeah.
What is the bracket in the integral that describes Ln? The curly bracket.
This curly bracket, sorry, it's not the Poisson bracket, it's the Schwarzschild derivative.
The Schwarzschild derivative, okay.
Yeah, so the Schwarzschild derivative itself generates, is identified with the generator of the diffeomorphisms.
Okay, thank you.
One way of understanding that a little bit is as follows, that if I give you a stress tensor, and the value of it, and I also tell you that it has a central charge, then you'll be able to find a coordinate system such that that value of the stress tensor that I'm giving you just as a function of little u is given by this coordinate big U. So in some sense, for any function t of u, I can always write it in this form. At least, yeah, there may be some minor restrictions on that function t of u, but for most general function, I can always find a function big U of u such that this is true. And then the proposal is basically the following: is that normally, if I do an integral, I would do a path integral. Suppose, I'm just going to do a little exercise. Suppose I have this Poisson bracket. And I have some Hamiltonian, h of p and q. Okay? And I want to compute trace of e to the minus beta h. Then the way I would do that is I would do the path integral times q dot, sorry, p times q dot. Because if that's my kinetic term, I will have that Poisson bracket minus h of p q. And I do that indeed by integrating from 0 to beta dt. That's the path integral formula for, and I require that these things are periodic with period beta. That's just quantum mechanics. Now suppose that I take h bar to 0 in this expression, okay? But I do that in a way where I'm also taking beta to 0, keeping h bar times beta fixed. So beta to 0 is taking the 0 temperature limit, infinite temperature limit. Then this beta times this 1 over, beta over h bar fixed. That makes more sense. So then this beta times that 1 over h bar still gives me a coefficient in front of h. But since beta goes to 0, basically what happens is that the periodicity in Euclidean time gets rolled up to a very small little, so I'm compactifying basically. I'm taking the Kaluza-Klein reduction, you call it, along the tau direction. And in this functional integral, the only thing that's going to survive, if you think about it carefully, or probably you have to do a careful reasoning, is the zero mode piece of this, the p. So I claim that this integral here will reduce not to a path integral, this is a path integral, to an ordinary integral over dp dq over phase space times e to the minus beta over h bar, which is now a finite number, times h pq. And this was my earlier claim, that in the h bar to 0 limit, if I want to sort of do computations that take into account, for example, the entropy, in the end I'm only interested in the volume of phase space, but it turns out that I can do this particular, I can evaluate this by taking the h bar to limit of that quantity. Okay. So this is a general fact in how to go from classical from quantum mechanics to classical mechanics. That this is. So this was actually the way in which in the paper with Turiaki and Mertens we were able to solve for this theory by using the fact that this path integral can be interpreted in this particular way, where this dp dq integral is this du integral, because as I said, I'm choosing some p and q's that parameterize my u. This h is that particular guy, this Schwarzschild. But actually, what I was doing, perhaps, was starting with a path integral in which I was actually quantizing this space. Now, if I would have written down the equivalent of this formula for that integral over u, where u is now no longer just a function that depends on the circle, But it also depends on another coordinate, which is the time coordinate here. Then I claim that this thing would have been obtained by using this abstract nonsense to say, hey, what did I do? I quantized diff S1 on this coadjoint orbit. I did it in such a way that I generated the Virasoro algebra, and I take the trace over the Hilbert space. Okay? I claim that this symplectic form then is the symplectic form that gives me the identity representation of the Virasoro algebra. And this thing is nothing else than the trace in the identity representation of the Virasoro algebra of Q to the power L naught, where Q is e to the minus that beta over h bar. And this thing I know how to compute. This is the identity character of the Virasoro algebra. And I already had it on the blackboard this morning. And if you use the fact that this is the identity character of the Virasoro algebra, it will depend on a certain way on that beta. And this, at least I could continue with the derivation. This is actually how one way of deriving this particular result. The one, okay, let me, instead of sort of continuing this story. So this at least explains the philosophy by which we were able to compute this particular potential function.
There's a question on the chat. Using Kirillov theory of orbit method, can you export this construction to study quantization of quad-joint orbits of BMS, say, in flat space holography?
Okay, that's a very specialized question. It's true that this whole formalism indeed makes use of this, what's called coadjoint orbit quantization. You can take any group here, and there's an appropriate symplectic form you can put on any group, such that if you identify the appropriate functions on that phase space, that these functions, according to the Poisson brackets of that particular object, will satisfy the symmetry algebra of the group. So it's always possible to write down an action of this form PQ dot. It looks more complicated than PQ dot, such that the corresponding functions that you take on phase space satisfy the appropriate algebra. So that's the general philosophy, certainly works. So this was used for Virasoro symmetry. This leads to the Alexeyev-Shadashvili action. And basically, part of the whole point here is that this thing is a dimensional reduction of that particular thing. And that dimensional reduction is motivated by this argument that in this particular limit, we're basically compactifying one direction of the functional integral in one dimension more, and we're using a two-dimensional path integral, or at least in this case, it's a one-dimensional path integral to a zero-dimensional, just ordinary integral.
BMS has the funny feature that you don't have an analog of Hamiltonian that's bounded from below.
So in the BMS groups, right? You may not have.
Yeah, these are a bit like induced representations. So you don't have. They're not highest weight. They're different. So they're not. They don't have a generator that's bounded from below, and that means that it's very hard to write a character.
Okay.
That is convergent. You can write some sort of formal character, and maybe it has some interpretation as a generalized character, but it's very confusing. So you could try to do it, but it's very confusing.
Right. Since we're talking about confusing, one thing that this business is all dangerous. So here I was trying to compute some e to the minus beta h just as an example of explaining what I was doing there. But I should have given you a warning. Let me call this the B tilde. beta tilde. And I think this is going to answer a question that Jan probably has in the back of his mind. I didn't change anything about the story here. I just called this beta beta tilde. The reason I'm calling it beta tilde is that this beta tilde is not the same as that beta. Give me a second. I guess indeed this thing here as a combination is called beta. The thing, geometrically, the thing that I'm trying to explain is the following. Here I'm integrating over a time coordinate t, and I'm shrinking that time coordinate in order to reduce this path integral to an ordinary integral. So I'm doing a dimensional reduction. But there's also another direction in this direction, in case I have this u as a function of u. So let this be u, and let this coordinate that goes around here be t. In order to start here, I start with a two-dimensional integral because I have a u that depends on little u, and I have this additional time dependence. So I'm actually integrating over, indeed, a cylinder, and indeed I'm going to get the vacuum character, but now I'm getting the vacuum character with the trace in this Hilbert space taken in this direction. This path integral also looks like a trace over a Hilbert space, and I wrote it like this as z of beta. And this is indeed also another trace over the Schwarzschild quantum mechanics of e to the minus some beta of the Hamiltonian of the Schwarzschild quantum mechanics. But this trace here is taken by taking the trace in this direction. Because the periodicity here is along the diff S1. Diff S1 sits in this direction. So indeed, and we're precisely again in this situation where in this direction, if I look at it, I had the identity character. So this is only true if I take this trace in the identity character. But if I have the identity character in this direction, in the other direction, I actually have all the excited states of the Virasoro algebra that are going here. So indeed, that's why this particular integral actually knows about all the excited states of the Virasoro algebra. So that's another sort of slight confusion in comparing these two. So the plan for tomorrow is we start afresh. I'll introduce the SYK model. So the SYK model is just a quantum mechanical system. You can write it down. It has Hamiltonian. And it's a beautiful, interesting system. It indeed has all these properties of maximal chaos. It has interesting out-of-time ordered correlation functions. It's a large N system, so you can use large N methods to study it. And rather surprisingly, it turns out that if you take the SYK model and it's formulated in a very different way in terms of Majorana oscillators, you can actually write down the Hilbert space. You cannot easily solve it for general N, but for N to infinity, it turns out that you can. And you can map it precisely into a description that has all these ingredients in it. So indeed, we'll see that the SYK model, although it starts out as really an ordinary quantum mechanical system, that you can actually see that it would have a finite discrete spectrum. But you can see that this sort of more geometric structure is hidden in it. So that's the plan for tomorrow.
About general CFTs, what happens when you act with conformal generators in the vacuum? Do you generate moduli space of vacuums or just excited state?
Good question. Does a CFT have a moduli space of vacua? For higher dimensional CFTs? Or are you asking about still two-dimensional CFTs?
For 2 or for 4?
Yeah. So let's say this way. Suppose I would put a CFT on a given space-time with a certain metric. Then even the choice of vacuum, if it's a general metric, is not unique. Only if indeed I have an appropriately symmetric space, like flat space or constant curvature space. Even for constant curvature spaces like de Sitter space, people have actually had a hard time identifying what they want to call the vacuum in the de Sitter space. So indeed, if for now I'll restrict to say flat space or anti-de Sitter space or things like that. In that case, I think once I give you the metric and it has these isometries, there's probably a unique vacuum state. But now I can indeed start acting with coordinate transformations on it, and then I get other states that locally might look like the vacuum state, because I can then go to the corresponding coordinate system. So indeed there's a pairing between a local vacuum and a local coordinate system. So in that respect, there's a moduli space of vacuum-like states that locally can look like the vacuum. One of the unusual things about two-dimensional CFTs is that almost any state that I give you, I can locally make it look like the vacuum. Even if I take a high energy state. So if I have some, again, CFT on the cylinder and I put an initial state that has a very high energy, I can actually locally find here a coordinate system so that this state looks like it's empty. So in that respect, there's all kinds of things that sort of locally look like a moduli space of vacua, but globally there's typically one unique vacuum.
At the beginning of the class, you showed a big picture of lower dimensional holography, and I've heard that the double scaling limit of a matrix model in a specific background is related to the JT gravity. So my question is, how is the matrix model related to the big picture?
Okay, very good question. Okay, so I'll repeat the question. So indeed, there's this very beautiful paper by Saad, Schenker, and Stanford, where indeed they considered a random matrix model, and they showed that if you look at that matrix model, indeed in an appropriate, you define it appropriately in a double scaling limit, you can do a 1 over n expansion, as Jan explained, that then can be mapped to a sum over topologies. This was part of their motivation. And what they showed is precisely that this spectral density that I've been talking about for the swatch in quantum mechanics, indeed I had this formula that rho of E is sinh of 2 pi squared of E. So this is what we call a spectral density. So what it means is that I should be looking for a Hamiltonian, perhaps, such that the eigenvalues of that Hamiltonian have a distribution that, as a function of energy, behaves this way: that e to the s of E or rho of s of E is the sinh. And it's known basically that if you write down a matrix integral, so what they're then going to say is that, hey, let's do the following. Instead of, a la Wigner, instead of taking one given Hamiltonian, let's look at the ensemble of all possible Hamiltonians that have this particular spectral density, at least such that the eigenvalues in the ensemble are governed by this, this spectral density. And then it turns out that you can do a genus expansion. And it turns out that the contribution to the partition function, or that the partition function of this matrix model splits up as a sum of contributions that indeed can be mapped to JT gravity. So you take this particular action, you put it on Riemann surfaces with arbitrary topologies, and maybe indeed asymptotically it might look like ADS, but you allow ADS now to have ADS2, but you allow to have an arbitrary number of handles. It turns out that the partition function of this JT gravity is basically given by the volume of the space of constant curvature metrics. If you have H handles, there's some moduli space, it's called, of the thing with H handles. You can compute the volume. You can sum over this. And there's a number that I can call 1 over, what number do they call it? Big L to the power 2 minus 2h. So you can write down this particular expression. And you can identify this thing as the partition function of this, this JT gravity, but in a quantum gravity theory where you also allow surfaces with handles. Okay? And it turns out that this thing indeed can be written indeed over as an integral over a matrix. Let me call the matrix actually H, for reasons that will become clear in a second. There's some appropriate potential that you can write down for H, and let me put a minus sign here. This V of H is precisely chosen such that the spectral density looks like that. So this is their amazing result. Is they said, so there's Mirsha Khani, she won a Fields medal. Wait a second. Okay, I forgot where the H goes. She won a Fields medal by computing these things. And then there is Orantin and Einard that were able to write Mirsha Khani's result in terms of a matrix model. So they had this particular equation. But the observation of Satz, Schenker, and Sandford is that the matrix model that these guys wrote down that does this particular sum precisely has that spectral density. Now, the reason for why this is actually very interesting, it's interesting for many reasons, I would say. But the reason why I find it actually quite interesting is the following, is that if, in the last, I guess, 70 years, people have been studying random matrix theory from all kinds of perspectives. And as Jan was mentioning, Wigner, although maybe earlier people may have had similar philosophy, but Wigner basically had the clever insight that if you want to do understand the spectra of nuclei of a very complicated quantum system, rather than actually trying to solve the quantum system, why did we look at general ensembles that have those kind of properties? And then it turns out that you can learn many things about just writing down the corresponding matrix ensemble. So Wigner indeed introduced matrices as Hamiltonians. Okay. 20 years later, at Hooft and other people started thinking about large N QCD, where the size of the matrix is the number of colors in QCD. And then at Hooft derived that the 1/n expansion of the matrices that are a matrix model version of gauge theory, and they have this expansion in terms of topologies. And at Hooft already identified those higher topologies with interacting strings. So in his mind, the Feynman diagrams of the QCD indeed were sort of some version of the large N QCD string. And then these would be the interactions of the string. The thing that's amazing is that this L, which is the analog of 1/n in at Hooft, is not the number of colors. This L is actually the dimension of the Hilbert space on which this H acts. So H is a Hamiltonian. It's a big matrix. And it acts on a huge Hilbert space. The size of the Hilbert space, so that L is the dimension of the Hilbert space. It's e to the power the entropy. At least it grows like the entropy. So therefore, suddenly, this whole topological expansion that at Hooft has introduced in the case of the large N gauge theory is now being applied to the Wigner random matrix theory. And previously, Wigner's random matrix ensembles and the random matrix theories that people introduced to do random triangulations and those didn't immediately have to do with each other. This to me is, in my mind, the first instance where people were actually doing random matrix theory in both versions of it, namely thinking about them as random spectra and then doing also a topology expansion. And part of the point of Stanford, Schenker, and Saad is that if you do a genus expansion, you're basically expanding in e to the power minus the entropy. So these non-perturbative effects, if you wish, they call them non-perturbative, but they're kind of perturbative from the point of view of the genus expansion. They capture that kind of physics. The mystery that, in my mind, people haven't sort of fully derived yet is the following, is that indeed if I now put wiggles on this boundary and I write down the corresponding JT gravity action and I would compute how it depends on the wiggles, I would get the Schwarzschild quantum mechanics. And I can again derive this thing from the Schwarzschild quantum mechanics. So in the Saad, Schenker, Stanford story, they basically got that answer twice. Once by matching this result. The other one by noting that if you go to the Lagrangian description of this thing and you allow wiggles here, that theory naturally has a spectral density that's given by the same formula. And I'll be honest, I don't know why that's the case. I haven't seen a first principle derivation of why these things came out the same. But philosophically, it justifies their answer, their suggestion that anything that's happening here with the topology really has to do precisely with these kind of effects. And their motivation, by the way, was precisely to go from a description where this thing was describing a continuous spectrum, and their hope to some extent was to say, hey, if I now actually make this number finite, maybe these these handles will give me information about the discreteness of the spectrum. And that's sort of, that's the Schenker-Stanford theory. And it indeed allows sort of, perhaps getting a little bit more insight in which kind of phenomena are sensitive to the discreteness.
Thank you.
Thank you for your lecture today. So the mantra of the matrix model side of this is to average over some distribution of Hamiltonians. Is there a reason to believe that each member of that distribution is a good QFT, is causal, unitary, whatever? And if not, should we worry about that?
Yeah, so the goodness basically of the UV theory at this point, and actually it's a very healthy attitude for most of these things, is to be agnostic about it. As I mentioned, tomorrow I'll be introducing the SYK model. And there you kind of have the same notion. It turns out that the SYK model, I can write down briefly, I could write down the Hamiltonian. It's a thing with coupling constants that tell you how a bunch of Majorana oscillators are interacting. Those coupling constants are called J. And it's quite important in that model is that actually that those coupling constants are random. They're chosen from a Gaussian random ensemble. And then you can have one of two attitudes. You can say, hey, I want to solve a given theory with a given one of these random numbers. Probably very hard to do. The thing that turns out to be easier to do is to basically, and this is then called the disorder averaging, is where you already include the integral over the random numbers over the Gaussian ensemble, and then suddenly it turns out that the computations become much more doable. It's a subtle question whether which properties of the individual element of the ensemble are well represented by the averaged quantity, behavior of the average theory. But it does turn out that for many properties it's true. But in some cases, you actually do get the wrong answer if you first average and then compute the quantity, or if you would try to compute it for the individual.
Because it seems from this point of view that like the spectral density that each of these Hamiltonians satisfies is the priority over any other facet of each given QFT, which sort of seems contrary to general notions in field theory of, we want things to have certain behavior.
Yeah, so I would say in this case the spectral density again is that's part of the theme actually of both Jan's and my lecture, I think, is that there are certain properties that are sort of universal and they're very, very robust once you push them in a certain extreme regime. There's probably something special about this particular spectral density, by the way, that has a certain universality. And the SYK model essentially has that spectral density. And the SYK model is indeed kind of devised in a way where it kind of seems to be maximally random. And indeed it has this maximal scrambling type behavior where everyone seems to want to interact with everyone else. So this is why you get universality. When we talk about quantum field theory, often we want to have more specialized features that we want to describe. So we put something in that captures a very specific phenomenon that doesn't sort of, is not fitting into this particular universal regime. So here we're very much focusing on the gravitational part of the whole thing. Right.
Thank you.
There's a question in the chat again. Is not Mizrahi's recursion valid for the WP volumes of moduli space of Riemann surfaces with geodesic boundaries, so that adding wiggles for the boundaries would take us outside the range of validity of Einard-Dorantin random matrix loop equations?
Okay, so it's the Wald-Petersen volume, that's the WP thing. So indeed, the thing I was talking about here is called Wald-Petersen. It's the space of constant curvature metrics on a given on a given Riemann surface. And it's true by allowing for the wiggles. Indeed, I'm not fully doing this thing in this way. Again, there's obviously a specialist up here asking these questions. The way you have to do this a little bit more carefully is you split out, you separate out this part of the calculation from this part of the calculation. So Mirshakani actually computed the volume of this region, summed over all the handles. You can do that if you wish. And then separately, you have to do this computation, which in my mind only enhances the question of why where both these calculations lead to the same spectral density. And I haven't found a first principle derivation. And actually, I haven't found a way of using the matrix model to derive that this quantum mechanics that sits on the boundary is actually the Schwarzschild quantum mechanics. If I would be able to take this matrix integral and somehow massage it or do something with it that would produce the Schwarzschild quantum mechanics, I would be very happy, because then at least I would start to understand why these things are the same. Yep. There's another expert over there.
Yeah. Well, maybe I can make a small comment. I'm not sure if this is a way of doing it, but this is a specific form of the matrix model, which I would say is like a color version of the matrix model. There is a different version with like which I would call a flavor matrix model, which is more like a Kontsevich type description of this model. Maybe there it's easier to see the Schwarzschild appearing. I don't know, but I think there are different ways of representing this matrix integral.
Yeah, that's a good suggestion. As indeed, you can do many things with this. It turns out that there are certain things, and I'm trying to remember what the name of it. I think it's called the normal matrix model. So you have certain matrix models that are kind of, it's a two matrix integral, an M and an M dagger, and you integrate and you require that they commute, I think. So you're integrating over a bunch of commuting matrices. And since M is now sort of complex, it turns out that the eigenvalue plane in this complex matrix model is a complex plane. And rather than then talking about a spectral density like this, you can ask, okay, where in the plane do the eigenvalues, are they sort of concentrated? And then it turns out that they're basically concentrated in some kind of quantum Hall droplet type thing. Yeah. And then it turns out that indeed the wiggles in the shape of this thing are described by a Schwarzschild derivative. So indeed, it's possible to get Schwarzschilds out of matrix models, but I don't know how to get a Schwarzschild out of this matrix model.
Yeah, no, that's right. But yeah, I'm just saying that there might be different representations of this matrix integral.
Right, that's
that
right.
are useful. Okay.
But indeed, this particular result indeed led to some of these questions that people had about whether you have to do ensemble averaging or not. But again, my attitude is the same as Jan had, essentially, where it's a matter of how you want to interpret the answers here.
So this is just a small question regarding the interpretation of the random matrix integral as a sum over surfaces, So it seems to me that if we consider just that random matrix integral without anything else, we won't get boundaries. We'll get closed surfaces, no?
Thank you. Indeed. So indeed, this is related to maybe the question that was asked up here. Is that there's a way of putting additional operators here that are called, and this thing then is actually something like this, or maybe you have to do Legendre transform this thing. So if you start, so you have this thing that's the matrix potential, And then in addition, you can introduce operators that actually look like this thermal partition function. And this is how you introduce boundaries. Because basically, once you have this object, if you start doing the planar diagram expansion with this object present, then this thing essentially can sort of start fixing the boundary. But it turns out that this thing then is more naturally associated with one of these loops that sits here in a specific location. I wouldn't know how to write down something here that would give me those wiggles.
Right, okay.
But I would know how to write something here that would fix the metrics to have a certain geodesic length of a certain boundary here. So I can have a hole with a certain geodesic length that doesn't fluctuate.
It's with the Laplace transform, no?
Yeah, I may need to Laplace transform to do that. So this is how I can go back, but I can start sort of gluing these things together. But thank you for the question. So indeed, in order to do this thing, I have to intersect that. That's right. Thank you. The answer, the thing that I wrote down would have been surfaces without any boundary. That's right.
There's one more question there. Is this entropy calculation related to the description of black hole as a Bose condensate of weakly interacting soft gravitons?
Okay. Depends on the definition of related. In terms of philosophy, I think there's probably some similarity in terms of how to think about the entropy of black holes. I do think, and I don't think this idea is necessarily new. It's pretty clear again that if you throw something into a black hole, it can be a compact object, but the way it's going to be returned when the black hole evaporates is in terms of very low energy. At least, certainly information that's being thrown in will be returned over stretched over a much longer time scale before you can see it back. So it's clear that in that respect, black holes are sort of like you can call them maybe a UV IR mixer, or at least they certainly are very much in tune with what's happening at long time scales. The idea that a black hole itself is sort of a condensate of gravitons, that becomes a bit of semantics. It's a solution to the Einstein equation. Whether or not you can sort of extract microscopic properties of the black hole by thinking about them as a condensate of gravitons. By the way, even that idea is not new. Bekenstein, who actually was the first one to actually think about quantifying what sits inside of a black hole, the way he derived the Bekenstein Hawking formula without maybe the pre-coefficient, but he basically got the area of the horizon already out of this, is by just asking, okay, well, hey, I have a black hole, but now I want to put something into it, and I want to put something into it so that I optimize the amount of information that I put into the black hole compared to its mass. And the way to do that is to try to fill it up with as low energy stuff as possible. And then he said, okay, well, the Compton wavelength of the particle has to fit within the black hole. And this is a very quick way of deriving the Bekenstein formula, is to just say, hey, what's the minimal amount of mass by which that I can add to a black hole by throwing in a particle? It's by taking the Compton wavelength of the particle to be the Schwarzschild radius. So the increase in the energy is 1 over m. And if I associate an additional qubit of information to every time I'm adding 1 over m, then the number of qubits is proportional to the area of the black hole. So Bekenstein already quantified the interior content of a black hole by essentially soft modes, if you wish. But in his case, he tried to still fit it inside of the black hole. I would say that if you think about it even more broadly, it could even be that much lower frequencies than the size of the black hole are still in play when you think about the entropy of a black hole.
Thank you. Probably just a super simple and naive question, but In the JT gravity model, you have the action in that board. What's exactly the role that the dilaton plays in that theory?
Okay, very good question also. There are various answers to this question. Let me start with a naive answer, at least one naive answer. What I could do is I could put this theory indeed on a circle. And then it turns out that the size of that circle, when I reduce the three-dimensional metric to a two-dimensional metric, and this action effectively can reduce to that action, where this phi is being interpreted as the size of the extra circle. Okay? Now, that's one answer. Now, let's imagine that I put a black hole in this space-time. Then the horizon of that black hole is a circle, because the black hole is, again, codimensional, at least, yeah, the horizon is a circle. Whereas a black hole in this space-time, the horizon would just be a point. But if I think about this black hole in the two-dimensional space-time as the dimensional reduction of this black hole, of the three-dimensional black hole, the entropy is proportional to the length of the circle, which is the area of the horizon, if you wish. Of the two-dimensional black hole, the entropy is equal to the value of the dilaton at the location of the horizon.
So in essence, the appearance of the dilaton from, let's say, I'm just using the word because I cannot find a better word, as I said, is following the same philosophy or idea of when we talk about gravity in higher dimensions and we make a KK compactification or truncation, I don't know. And from that compactification to one dimension less, that's why the dilaton is appearing. But in this particular case, in 2 dimensions, the dilaton will play an essential role in giving us the entropy. That's what you said, right?
Yeah, so it's true that if you go from higher dimensions to lower dimensions,
Mm-hmm.
If you're still in higher dimensional gravity theories, you can go to lower dimensional gravities, and then basically the Newton constant in lower dimensions always involves then the size of the extra dimensions relative to the Newton constant in the higher dimension.
Gotcha. Okay.
But once you go from 3 to 2, there's nothing else left, again, in terms of writing down an Einstein term anymore.
I see.
And it becomes essentially, it becomes then essential that the coefficient in front of this thing is actually a field.
Mm-hmm.
Let me make one other comment. Suppose that I would add a matter action here.
Okay.
And I would derive the equation of motion of this action.
Okay.
You get something that the second derivative of the dilaton is the stress energy tensor.
Okay. Okay.
And which I can integrate basically once at least. Something like this, where the derivative of the dilaton is the integral of the stress energy tensor.
Mm-hmm.
And it turns out that this equation is actually indeed the equation that you can derive if you are asking about how the entanglement entropy of a certain region outside of the black hole changes when I throw something into the black hole. So indeed the equation of motion of the dilaton gravity theory indeed wants to identify phi literally with an entropy. So you can really rather microscopically almost understand why this thing is counting for an entropy.
Mm-hmm.
Another reason I should mention is the following, is that if I would insert phi at some location, or let me be more precise, if I put phi at some location in the exponent here, and that actually let's assume that this location is the horizon, and I put some epsilon in front of it. What happens then is that the equation of motion no longer tells me that r is minus lambda, so it's no longer constant curvature, but r has a delta function curvature at the location of the horizon. So at that point, indeed, I've inserted a little conical deficit.
Okay.
And that you can use that kind of argument to basically essentially use thermodynamic reasoning to tell you that conical deficit indeed is like differentiating respect to the inverse temperature, because for a black hole in Euclidean space, the periodicity around the horizon is fixed to be 2 pi in order to have the
conical defect,
not have a conical deficit. So there's this whole argument basically that inserting a dilaton at the horizon indeed is in that respect also
to
again,
fix that. Okay.
Geometrically computing the entropy.
Okay, I see. Thank you.
Any more questions?
Sorry, just last very simple question. So, from your presentation of Schwarzian quantum mechanics, I mean, what's really special about it?
Okay. What's special about Schwarzian quantum mechanics? So the SYK model is indeed it actually arose in an interesting way. I should mention this. So Wigner introduced random matrix theory sort of in the 50s to understand nuclei. Then actually in the early 70s, a bunch of people wrote down actually already what we would now call the SYK model. The SYK model was already written down in the early 70s. I keep forgetting what it was called. It was something called, okay, I forgot the name for it. But they wanted to use the SYK model as a model for nuclear physics, which is not bad, because a nucleon is actually a pretty good model for a black hole. You throw a proton into the nucleon, it scatters around for a very long time, it stays there for a while, and eventually the nucleon will decay. And therefore, indeed, they wanted to have some kind of random model, and they imagined that inside of the nucleon, two things could interact, could collide, and then produce two other things. So they had a 4-body interaction with a random coupling, and they already had a Gaussian random coupling in their model. Early 90s, Sachdev and Ye introduced that model because they just liked the idea that it was sort of an all-to-all quantum mechanic, quantum many-body system. And then Kitaev had a very deep insight, indeed, essentially following sort of some of these calculations that were exhibiting this Lyapunov behavior that Jan also talked about, where he thought, hey, okay, now let me try to find a quantum mechanical system that has this Lyapunov behavior. And then he indeed started doing computations with this SYK model. But then he had indeed this insight that in this theory there is indeed sort of an emergent reparametrization symmetry, and he kind of knew that reparametrization symmetry could not be exact and it had to be broken. But then he also could argue that whatever the action was that described this reparametrization mode would have the invariance under these Möbius transformations. So the transformations, and I think I now erased them, the A tau plus B divided by Z tau plus D, this was a symmetry that he knew that the action needed to have. And then, so what the Schwarzian is, it's the thing with the fewest numbers of derivatives. That's it's an action of that depends on a diffeomorphism, and it's the action with the fewest numbers of derivatives that preserves the Möbius group.
Sorry, that preserves.
It's called the Möbius group. So this A tau plus B C tau plus D.
Okay.
So this particular invariance needs to be preserved. And if you want to write down an action that's invariant under this, the simplest action that you can write down is the Schwarzian.
But for example, in that integral, but also on the action that you presented first, so I'm just thinking that from the moment that you told us that that Schwarzian derivative amounts to that generator of time translations, but like, where are the microscopics of the theory? Like, where are they conveyed, like, specifically?
Okay, also a good question. This is a more general question about effective field theory. So if I give you a UV description, so the question is indeed, why is the Hamiltonian of the Schwarzian actually identified with the Hamiltonian of the UV theory? This happens all the time in physics, meaning whatever we use as the Hamiltonian that we want to use to describe low energy, say the standard model Hamiltonian, we think about that standard Hamiltonian as a pretty good description of the Hamiltonian of our world. But we don't know what the actual string theory is, or the actual complete theory that describes our world. So we don't literally know what the Hamiltonian is of the UV theory. But whenever you have identified sort of an effective description that's valid at low energy, and you have identified the low energy degrees of freedom that are essential, then the Hamiltonian of the low energy theory is indeed not identical as an operator with the UV Hamiltonian, but it's still true that both of them describe the same time evolution. But the Hamiltonian of the Schwarzian describes it in the space of modes that are sensitive to the Schwarzian degrees of freedom. But it's still true, and this is where your question goes, is that I'm not losing any energy in integrating out the UV degrees of freedom. I'm keeping track of all the energy. I am losing entropy, though. So there, indeed, in the entropy of the Schwarzian, which I can compute, which I wrote down, it actually is not fully, there's a pre-coefficient here, which I should have written down, in the SYK model, which is e to the S naught. And S naught is a prefactor that depends on the SYK model, and the SYK model can compute S naught. The Schwarzian model, the Schwarzian theory cannot. So there is indeed information in the UV theory that the IR theory doesn't know, but there's no energy in the UV theory that the IR theory doesn't know, because all the energy sits also in that Hamiltonian.
Okay, thank you.
All right, I think that's probably enough for today.
Okay.
So let's
Thank you.